Basic area interpolation, or the basic areal interpolation technique. So there's many variables that are represented at what we call ecological levels. These are variables represented in areas, like counts of population, of denning sites, and things like that. And that's called the ecological level. Unfortunately, when you're doing an analysis with multiple layers, sometimes the variables that you're working with, or the mapped layers, have a geography, that is a spatial configuration of area units, that is different from the target of your analysis. So for example here, we have source data boundaries here at the DA level, that's dissemination area level, it's a census unit, the smallest level of census geography at which the full census is available. And for example, here we have maybe population, and you can see that population differs in different units according to color here. But we have to we may have to analyze that at boundaries which are very different. For example, here, the neighborhood boundaries. And you can see there's a mismatch, right? In that, somehow we need to get the data from this level, the DA level, and these polygons into these larger polygons. Or sometimes it could be to go to smaller polygons as well. But we can't go directly because there's nothing in common between the two sets of polygons. They don't share the same boundaries anywhere. Here, another example, we have species counts of different trees in a forested region. And we can see we have polygons representing each of these little forest patches. But we may need to analyze that data with other data that we have at another ecological scale. Here, for example, the block unit. And so somehow we have to get data from here into here. And how do we go about doing that? That's the answer. Well, we'll find the answer in basic area interpolation. So whenever we have a zonal geographic mismatch, we need to use basic area interpolation as one technique, and this is the least accurate technique, by the way, of getting data from one level of geography, one zonal configuration, that means polygon configuration like we see here, into another zonal or polygon configuration here. In both of these cases, we have the target areas where we need to do analysis within. These are larger, so these are larger polygons. So there's both a zoning difference and a scale difference. Because scale is the size of the polygons, the original ones at the level of which the data is collected are smaller than the target ones over here. So that's a scale issue, and zoning means that the boundaries aren't the same. And so whenever that happens, we need to use some sort of areal interpolation technique in order to get our data into the target area boundaries up here. So the terminology then of basic areal interpolation is that we're transferring area data between two different geographies. And again, that means two different zonal configurations. And that requires area interpolation. And we have what are called source zones. Here, an example is dissemination area. So these are the little dissemination areas like we just saw. There's one there. You know, there's a small one here. You can see the whole thing is a tessellation of irregular polygons. So that can be our source zone. And our source zone is the data or the layer that contains the data we want to have reallocated to a different zonal configuration. And that different zonal configuration are called the target zones. For example, here they could be neighborhoods as an example. And so both the boundaries are different and the sizes and shapes of things are different. So if we look down here, we see that the red lines are the target zones, and those are just put on top of the source zones to show the mismatch between those two geographies. Some cases, we might have a bunch of them fit in fairly well, but in other cases here, like this one, well, it transverses or intersects a number of different source zones. So we go from source to target through a process of areal interpolation. And again, a different geography, when I say something is a different geography, all I mean is that something has a different zonal configuration where the boundaries or sizes have changed and are no longer the same as the original source features. This is the equation for basic area interpolation, and it may look a little intimidating at first. So let's look at it step by step here. Let's just take that part away to start with and just look over here at this part. Here, this term, the numerator, is the area of the source polygon intersected with the target polygon. So that means there's an intersection operation up here. Divided by the area of the source polygon that was intersected with the target up here. So that's called an area ratio right there. It just tells us how much, when we intersect two polygons, the source and a target, it tells us the proportion of the original source polygon that is within the new target area. Then we have this here, xi. That's the count of the source zone. So that's the variable that's measured within the source zone. It's being reallocated to a new geography. And the summation here is over I. So however many intersections there are between the source and the target for the original source zone I, that's the sum over all of those. And then that gives us here AT, which is the target zone count. It's very simple in practice. It requires one single operation, a field calculation to get that, and maybe a second field calculation for that part, and then a summation one, a summary table. Now, the reason we can do this is because of the basic assumption of areal interpolation and the basic assumption of ecological data. So data, any data that's measured within a region, we assume and have to assume that it's homogeneous. That means that it's equally distributed across the entire polygon in which it is observed or measured. So that's the assumption of all ecological level data. We know that's not true in many cases, depending on what we're looking at. We know space is not uniformly, or things are not uniformly found in space. Even temperature, whatever you're looking at, it's not uniform. It changes from location to location. Things, of course, that are closer by are more similar than things further apart. We know in the real world, though, that we do have an inhomogeneous distribution of things. So if we had these 9 things here, in this case, that's our assumption that those 9 things that we counted are homogeneous in this area, and that means if we cut the area by 2, we would divide the 9 features by 2 and allocate 4.5 here and 4.5 over here. We can do that because of the assumption. We don't know the degree to which it is homogeneous when we only have a polygon and a number to work with. We know that there's probably an inhomogeneity. That means that there's clusters or gaps within the distribution of things that are observed in the polygon, but we don't know where those are. So we must remain, for now, with this assumption. And we'll see how we can integrate inhomogeneity when we look at dasymetric mapping, and as a step within the basic area interpolation process. So here we have a target zone which gets values assigned to it. It's a sum of all of the source values times how much of the areas they were in that intersected with the target area. Here's a worked example. So here's our source region at the top. It's a 1 by 1 kilometer square, and we have, of course, a homogeneous set of values. Each value is 1 unit. So that's 1 unit, that's 1 unit, that's 1 unit, 1 plus 1 plus 1 plus da 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 plus, right? And then we could just say 1, 2, 3, 4 by 1, 2, 3, 4, 5, 6. So 6 times 4, right, is 30. 6 times 4 is 34. So there's 34, or no, it's 24, sorry. 6 times 4. 12 and 12 is 24. Yeah, so we have 24 things in that original source geography. Then we have a target geography, which is this new rezoned region. One zone up here takes up 1/4 of the area, and the second zone is 3/4 of the area. So we can see that if we have 1/4 of the original area times 24 would give us how many things will go in here. So 1/4 times 24, and this one would be 3/4 times 24. It's pretty straightforward how that works to figure out how many of these 24 objects will be allocated to each region. So here's our target geography counts now. We have 1, 2, 3, 4, 5, 6 here, and we have 18 over here. So 3/4 times 24 and 1/4 times 24. And we end up with then these two new target regions with the appropriate counts within them. And that's just worked out over here. So again, we looked at the equation. We note the total of the source region, 24. The area of the source region, which is 1 square kilometer, because we need to know that term there. And then the intersection of the area, 1. So area 1 intersected with the target right here, and that's 0.25 square kilometers. So that intersected area is 0.25 square kilometers. And for this area here, intersected with the source, is 0.75 square kilometers. And then we just do our, our sum here is pretty straightforward because it's only going from 1 to 1 for each of the target regions, A1 and A sub 2. So 24 times 1/4 over 1 is 6 people, and 24 times 0.75 over 1 is 18 people. Or things, objects. I'm just calling these objects people, just to make it realistic. So that's how that works. That's a basic area interpolation. So again, area 1 and area 2 are the two new target areas, and each of those has a intersected region size, 1/4 times 24 equals 6, and 3/4 times 24 equals 18. Now, this is what we call a pycnophylactic interpolation. So here, PYCNO, pycnophylactic. Pycnophylactic means that it's a volume-preserving type of interpolation, in that if the in count is 24, the out count is also 24. So if there's 24 things going into the process, 24 things must come out of the process. And that means it preserves the volume. So it's a volume preserving technique, basic area interpolation. And therefore it has the quality of being pycnophylactic. Now, in terms of a procedure, we can look at it this way. We have a simple GIS procedure for basic area interpolation. And it follows this equation step by step. First, we start with this. Calculate the original source zone values of area. And you must calculate them in a field that you create that is not part of the shape area field itself. Because remember, shape area is a field in every feature class's table in a geodatabase if it's a polygon feature class. And the numbers within the shape area field always reflect the current areas of the polygons for that layer. And so those will change if you do an intersection with the target geography. You can't then use those areas any longer as, in other words, they disappear. So the original source areas disappear because now the shape area field would contain the intersected areas of each of the polygons instead. So we must store in our source attribute table a field which we might call original area, for example, orig area or something like that. And that won't change, and that will remain as the original area throughout the processes that we're going to do. So that's the first thing we do in the equation is we get the terms. So we get that term, which is a new field in the source table. Then we get this term, which is a new layer. We intersect the source and target layers. And that creates a new layer altogether. And that new layer contains the information about the original areas, and the shape area field contains the intersected areas. And all we need to do next then is do this part, which is a new calculation in the intersected A intersect T, so source intersect target table, where we multiply our original counts times the intersected area, the shape area, divided by the original area. Then we use the summation of them all. We now use a summation over, or a dissolve operation, where we dissolve the intersected layer by the target layer identifiers. So these are the IDs of each of the target polygons, or some unique identifier for each of the target polygons. We say, okay, dissolve all the boundaries between target polygons with the same identifier while summing up the field that we created here. And then we're finished with basic area interpolation. Here's a cartographic model that just shows the process, and we'll look at it step by step. So look at the top of that first. Here we have this is our source region. That's a source. And then we create a new field called source area. So we're adding that field, and now in here we have our original source with a new field. Then once we have that new field, I'll have to get that part done. We have our forest cover, our source again, with a new field, and then we calculate field. So in the into that new field, basically, we just bring in the shape area field. So into the source area field, we bring the shape area field. We just copy the values over by you'll see clicking on them, and that then creates our next step of the process, where we now have a source area field within the table. So there's forest cover with a source area field in it, or original area, you can call it either one. Then we have our target here. So now we intersect these two, so that we use the intersect signs, the logical sign for intersects right here. So we intersect source, which is forest cover, which with that new source area field in it that won't change, with blocks, which is the target. And each block has a unique identifier. And we intersect. Then we have an intersected layer that we work with. So with the intersected layer, now we have to calculate the equation, basically. The value, the number of trees, times the area ratio. So here we have our intersected layer. We give a field name called AT right here. So we add a field, then we have block, so we have a new field with called AT in here. And A sub T again, remember, is the equation, the part of the equation we're trying to get to, A sub T. Here we have then an expression, which is the shape area divided by the source area times, in this case, it's called balsam fir, which is the number of fir trees in each of those forest plots. And that goes into the field name AT, calculated. So now we just have to do the summation part of the equation. And that's done through a dissolve operation. So we say, okay, for the DBUID, which is the block identifiers, so that's a field that uniquely identifies each block. Any field with a unique identifier for each of the original target zones would be fine. Then we say statistics sum the field that we created previously that's in this table, basically the A sub T field. Sum that while you're dissolving, and output then, the output will be the target geography with counts of balsam fir. Balsam fir trees. And that looks like right down here. So we went from that to here, and then from that to there. It's a long cartographic model, you know. It's just to show you the steps cartographically. And that it could be done that way if you so choose to do it so with a cartographic model. To undertake a basic area interpolation, we start by calculating the source area of the source polygons. So we add a field to our table for the source area, which is the forest cover that we're talking about. So we just call the field source area, and that's to distinguish it from anything called shape area or any other area that might already exist in that table. Then the source area is also of type double, by the way, right? Because any numeric columns or fields we're adding to a table will generally be double if they're capable of holding decimal places. Next, we calculate in that field the shape area. So all we do have to do is say, okay, well, forest cover, we choose the source area field. Then we scroll in the fields to find the shape area, which is again the shape or the area of each polygon in the current coordinate system within the geodatabase feature data set. Then we just say copy it over by double clicking on it, and it will put it into the expression box down here. And that will then calculate the areas and get this part of the equation right here, the denominator. Now, for this particular step, you could also do calculate geometry attributes. So that's another thing you could do instead of calculate field. So you could say calculate geometry attributes. Same thing up here would be for that. But then down here, afterwards you'll see an example later on. But you would choose then to calculate the area for that source area field, and it could be area in the current coordinate system, the native coordinate system of the spatial data layer feature class, or geodesic area, the area calculated using spherical trigonometry, well, spherical-like trigonometry equations of the area on the ellipsoid. Next, we want to get this, the area ratio, the area of intersection between the source and the target for each of the source and target zones. So we do so by intersecting the forest cover and the blocks. The blocks are again the targets. So we have our source and our targets right there. We'll call the output feature class blocks underscore forest underscore isect to remind us that this is a blocks forest intersected. And you just basically have to click run. That then produces inside the new intersected layer table. So a new feature class is created, and it has a table. And in that table, you'll see the source area field, which came over from the forest cover source area field. And then you'll see also a shape area field in here, which is the current shape area of the intersected polygons. And you'll notice that, for example, if I was looked at the source ID of 172, so polygon 172 in the forest cover had the original source area of 7,221 square meters. And it's repeated twice here. And that's because two parts of that original polygon, 172, were intersected by the blocks. And that's why it's shown twice in here as two original source areas. Whereas the new areas are right here, the shape areas. So part of that original polygon, 6,505 square meters of that 7,221 square meters are in one intersected polygon, and 715 square meters are in the other intersected polygon. And that's what the intersection does, is it gives us that information. The current area of the forest cover polygons that have been cut up by the blocks. And we have the original forest cover area each time. So now we can complete this part of the equation. The forest cover count, and we'll be looking at balsam fir, times the area ratio, which is the shape area that as it exists right now, the intersected one, divided by the source area. So within the blocks forest dissect table, we add a new field called AT. That's this thing here, right? That's what we're doing. We're not doing the sum yet, but we'll still call the field AT for A sub t of double. Then we calculate in that field the expression here, which is the balsam fir, which is in the fields here, times, and then in parentheses, shape area divided by source area. That's this part right here that's happening, right there. Next, to complete our reallocation of one geography to another using basic area interpolation, we have to do a summation of the AT field that we created by target zone identifier. So we use dissolve for this, the dissolve tool. So we dissolve the intersected layer by the target identifier. So these are the unique identifiers, DBUID right here. So it's a unique ID for each target zone. So any unique ID will be fine as long as it identifies each of the target polygons uniquely. And we'll call the output here areal interp, and it will have the same geography as the blocks afterwards. The final thing that's very important, and you can see here that's just the DBUID is the dissolved fields. We never use source ID. Okay, source ID is something that is only internal to the geodatabase. It does not uniquely identify anything from other tables or anything like that. Only uniquely identifies the current one, which is an intersected one, which wouldn't have been any use to us. We need to sum up the AT values by their block identifier right here. So you can see all these ones are the same block identifier. So all of these ones right over here would be summed together, and any, of course, that are below there. So that's the AT field right here. And we say sum that field. So you must choose a statistic type, and it must be sum. And then you can click run. The output in the areal interp table, you'll see a sum underscore AT. And that is the total number of balsam fir trees within each of the new blocks. And this is also, and you'll see how to do this in Python within the exercise, but for here, you can see it's the same process. And whenever we're doing something, a complex equation, we do it term by term. We get the term, so we start by getting that term, just like I showed you manually, right? So that's adding a source field and then calculating the shape area in that field. So source area field gets a shape area. Then we do the intersection up here. We intersect the source and target. So we use the intersect tool. And in here we put a list of the things we want to intersect. Source, target, where source up here and target up here are strings referring to the source and target layers within the table of contents. And it's nice here when you say source and target because it makes it easier to keep straight as you're going through your code. So you give forest cover to source and blocks to target. Then you only have to talk about source target after that. You don't have to remember which was blocks and which was forest cover. It's all taken care of that way. So that is intersected. And the output here is just an intermediate one called sit, S-I-T. Then we do that equation, part of the equation right there, before the sum. So we add a field like we did AT using add field. The expression we put here as a single, or as an expression, which is a single quote, and then the entire expression that goes in the calculator, and then single quote again. So we actually write out that calculator thing here. Then we say calculate field. We bring in sit, which is this one, which also contains that. So that's that part there. So sit with the new AT field, and then the expression right there, so EXPR, which is coming from right there. And of course you could write it in here, it just makes it longer of a statement. And Python, to make sure that it's a Python expression we're using. So that creates inside the SIT variable, or layer, the AT column. Now we just have to dissolve and sum the AT column by the unique identifiers for each of the target zones or blocks. And that's this part here, the final part. So we use the dissolve tool. We say take in sit, the AT field. This is the unique identifier field. And then we want to do the AT field summed by unique identifier. And that's it. And that's, of course, as will be explained with comments and detail in the exercise 9. That's just to show you that we can do the same thing in Python relatively quickly. The advantage of Python, of course, over doing it manually is if you want to change something, or just change, let's say, the source and target to do different layers, you just have to change those two things up here. And you can rerun the whole thing and get another basic area interpolation done. So finally, how do we determine whether or not what we just did is correct? Well, we use basic logic based on the knowledge that this is a dasymetric technique. It's a volume preserving technique. And remember, that means that whatever the numbers that are going in from the source zones, the sum of those must be the same as the sum that comes out the other end in the target zones. So in this case, we were looking at balsam fir. So we open up the forest cover table. We look at the balsam fir column, and we do statistics. So how many are there in there? And we find there are 52,800 in the forest cover one. Then that number should be the same number that we get out of the area interp table at the end by summing the sum AT field. And that one is 52,793. So they're almost identical, right? So there's a difference of 7 trees over the process. Some of that could be rounding or precision issues, but in this particular case, the reason I get that is because I used inside the when I did the forest cover source area, I used the geodesic area. And so that's why it comes out slightly different, because I'm then dividing afterwards an intersected area, which is in units of a UTM zone, by a geodesic previous units. And so it gives a little bit of a difference. So you could say that, the uncertainty induced by geodesic versus a UTM zone calculation of area is about 7 trees in this case. But as long as your numbers are very close together, then you're fine. But ultimately, they should be, identical to within a decimal place. But this is fine because I know what I did and why that is. If it's happening to you, now you must go back and find out, well, why is that? Why aren't they the same? Because that's an important thing to be able to figure out. Because it means either something is wrong, or you did an incorrect procedure, or could be anything. Sometimes they might not be the same because the source and target geographies aren't the same. So they don't, in this case, they match pretty much perfectly. But if they don't, then you might have a different number going in than coming out in some cases. But you need to find that out to explain why there's a difference. And that's the ad hoc validation procedure. Ad hoc just meaning on the fly, just made up to figure out whether or not what we get is right. So there are some problems with mapping data in areal units in general. So one is generalization, that areas with and without the variable interest are combined into a single polygon. And that just means that if this was, for example, our source zones, well, we could look at one of these polygons. It's right here, or right there, in fact, not that part. So that's one polygon. That one polygon, we know, has a number of things in it, which could, let's say, be 10. And we assume that that's homogeneous. So it's a homogeneously distributed thing, object. With the 10 people, well, the 10 people are standing equally apart within that polygon. Now, we know that's not real, right? So we can't know anything about subunit variation of the geographic variable of interest when we work with area data, because with area data, we have to follow that assumption. And the problem with that, of course, is when we start to look at things like density measures, like population density, for example. Well, the population density of this entire polygon might be 0.1. Let's just say it is 0.1, okay? And that's because we use the entire area. Density is people or thing over area. Now, we use the entire area because we have to assume homogeneity of the distribution of things. Now, if we knew something about the subunit variation, it might be the case that, well, within here, all the people just live in a small little part of that region, like right there. And that would mean the real area here is much smaller than the area of the entire polygon. So we would still assume that if we knew that they all lived here, they're homogeneously distributed in that area, but that would mean our population density might be something like 0.89 for this region instead of 0.1, simply because area changes right there. If the area becomes smaller, the density increases. If the area becomes larger, the density decreases. So if we knew something about the subunit variation, we could get a more accurate measurement of things like the density of whatever things we are counting within these area-based polygons. A third issue with area data like this is the modifiable areal unit problem, the zoning effect, which I talked about earlier in this same module. That changing area unit boundaries, even without changing their sizes, just changing the boundaries around relatively so that everything still has the same size that it did before, would change the mapped result, even if you're using density or whatever measure you're using, because you're now moving around the boundaries of things in space without, you're changing that spatial configuration or the geography of those things. And of course, if you include size in there, size plus the zoning, the way the boundaries are configured, you can get very different results as well. And that's something that's done very commonly particularly by the Republicans, ICANS, in the USA, through gerrymandering. So gerrymandering is that process by which voting districts have their geometry, their zonal configurations changed to favor outcomes in elections. So, for example, you may have a region that has Democrats and Republican voters, and you may want to split, if you're Republican, you'd want to split that Democratic one so that it would become a region that has a majority Republican or something like that too, and that helps ensure the outcomes of elections, free elections, in the Democratic regions, and that happens everywhere. That also happens in Canada with electoral districts and stuff like that. And that's the modifiable area unit problem in action. It's a problem for analysis, but it's also a tool that's used by certain people for manipulating spatial data and spatial outcomes.